Have you ever stopped and thought about this? Every time a commercial jet lands, its landing gear absorbs an impact force of over 300,000 pounds in less than half a second. That's the weight of 6 loaded school buses, slamming down onto 2 thin struts of steel and hydraulic fluid, hundreds of times a week, on the same aircraft, and somehow, it doesn't bounce, crack, or collapse. The secret isn't strength, it's not steel, and it's not brute force. It's a chamber of compressed nitrogen gas, a tank of hydraulic fluid, and one perfectly tapered pin. Today, we're breaking down the strange engineering that turns that kind of violent impact into a smooth, routine landing. I promise, after this video, you'll never watch a plane touch down the same way again. To understand the importance of this pin, we first need to appreciate the physics of a landing. Imagine a huge airliner, let's say a Boeing 777, coming in at over 150 miles per hour. The kinetic energy it carries is staggering. To put that in perspective, the energy isn't just from its weight, but from its speed, squared. Now, it's important to remember that at the exact moment of touchdown, the wings are still generating a lot of lift, so the gear doesn't have to support the entire aircraft weight instantly. But even so, without a system to absorb and dissipate that massive energy, the aircraft would have an extremely hard landing and could bounce violently off the runway. This wouldn't be like a basketball bouncing. It would be an uncontrolled rebound that could cause the pilot to lose control, potentially leading to a runway excursion. The forces could be high enough to cause serious structural damage to the wings or fuselage. In aviation, simply using a solid strut or a basic spring is not an option. The forces are too great, and the need for control is absolute. So, engineers turn to a solution that combines a gas and a liquid to tame these incredible forces. The hero of our story is the oleo-pneumatic strut. It's a sophisticated shock absorber that looks like a simple piston, but operates on brilliant engineering principles. Its job is to do 2 things: absorb the initial shock of landing, and then dissipate that energy to prevent the aircraft from bouncing. Think of it not as a spring that just stores energy, but as a brake that converts that energy into something else. In this case, it converts the kinetic energy of the impact into heat. This single device, often just called an oleo, is responsible for dissipating a huge amount of the landing impact energy, turning what would be a brutal jolt into a firm but manageable touchdown. It does this by perfectly blending 2 distinct physical principles within one sealed cylinder: the compressibility of gas and the resistance of liquid. It's a pneumatic hydraulic system, and understanding how these 2 parts work together is the key to unlocking the secret of smooth landings. Inside every oleo strut are 2 telescoping cylinders. The upper cylinder is fixed to the aircraft structure, while the lower cylinder, or piston, is attached to the wheel assembly and slides inside the upper one. The upper chamber is filled with an inert gas, almost always dry nitrogen. Nitrogen is used instead of regular air because it lacks moisture and oxygen, which prevents internal corrosion and ensures consistent performance across a huge range of temperatures. If there were water vapor in the strut, it could freeze at high altitudes, turning the strut rigid, or boil from the heat of landing, causing unpredictable pressure changes. This chamber of compressed nitrogen acts as a powerful, endlessly reusable spring. When the aircraft touches down, the strut compresses, and the nitrogen gas gets squeezed into a smaller volume, absorbing the initial shock. But a spring alone would be a recipe for a bad landing. It would store the energy and then release it, wanting to push the aircraft back into the sky. That's where the second part of the system comes in: the hydraulic fluid. The lower chamber of the strut is filled with a special hydraulic oil. In many designs, separating the gas and the liquid is a plate with a small, precisely engineered hole in it, called an orifice. As the strut compresses, this hydraulic fluid is forced from the lower chamber, through that orifice, and into the upper chamber. Forcing a thick fluid through a tiny hole creates immense resistance. It's this hydraulic resistance that acts as a damper, slowing the compression and converting the energy of motion into heat. The fluid actually gets hot, and that heat is then safely dissipated through the metal casing of the strut into the atmosphere. The gas acts as the spring, and the fluid acts as the brake. Together, they absorb and get rid of the landing's energy. But that leads to the real question: How does the strut provide the right amount of resistance at the right time? The problem with a simple fixed hole is that the resistance it provides is constant, but the forces in a landing aren't uniform. They change as the strut compresses and as the wings gradually lose lift. To manage this, the system needs to be smart. It needs variable damping, stiffer when it needs to be, and softer when it doesn't. This is where our tiny, unassuming hero comes into play, the metering pin. The metering pin is a long, tapered rod of solid metal that sits directly inside the orifice. As the strut compresses upon landing, the metering pin is pushed up through that hole. Because the pin is tapered, it might be wider at the bottom and narrower at the top. It changes the effective size of the orifice as it moves. At the very beginning of the touchdown, when impact velocity is highest, the strut is mostly extended, and the shape of the pin allows for the largest gap. This provides a softer initial resistance to avoid a jarring impact. As the strut compresses further under the aircraft's weight, the thicker part of the pin moves into the orifice. This progressively restricts the flow of hydraulic fluid, making the damping stiffer and smoothly bringing the aircraft to rest on its suspension. It's a completely passive, mechanical feedback system that ensures a smooth, controlled absorption of energy. There are no computers here, just pure physics. It is, without exaggeration, the component that orchestrates a smooth landing. So, what happens if this critical pin fails? Let's explore a couple of scenarios. First, imagine the pin shears off. If the metering pin breaks, it can no longer restrict the flow of hydraulic fluid. The orifice is now effectively wide open. Upon touchdown, the fluid would rush between the chambers with very little resistance. The entire damping function of the strut would be lost. All that's left is the compressed nitrogen acting as a huge, uncontrolled spring. The strut would compress violently and then rebound with enormous force, creating a pogo stick effect. This could cause the aircraft to bounce hard down the runway, potentially leading to a loss of control, a collapsed gear on a subsequent impact, or severe structural damage to the airframe. The second scenario is a pin becoming jammed in the orifice. If the pin gets stuck in its most restrictive position, it could almost completely block the flow of hydraulic fluid. This is sometimes called a liquid lock. Since hydraulic fluid is virtually incompressible, the strut would become extremely stiff. There would be almost no shock absorption. Landing on a locked strut would be like landing on a solid steel bar, transferring the full, brutal force of the impact directly into the airframe. While landing gear is built with huge safety margins, this would put immense stress on the gear and its mounting points, risking serious damage. While a metering pin failure is a scary thought, it is incredibly rare. These components are engineered to withstand immense forces and are inspected regularly. When landing gear does fail, it's more often due to other factors. Things like metal fatigue and corrosion are constant enemies. Fatigue cracks can develop in steel components after thousands of landings. Corrosion can weaken parts, especially in aircraft that operate in humid or salty coastal environments. Investigations have also shown that a significant number of landing gear issues are linked back to improper maintenance, whether it's using the wrong type of fluid, contamination getting past seals, or mistakes made during an overhaul. A tiny piece of debris, or using contaminated hydraulic fluid, can cause seals to fail or valves to jam, leading to a system malfunction. This just underscores the absolute criticality of the rigorous maintenance and inspection schedules that every single aircraft adheres to. The engineering that goes into every component of an aircraft, from the largest wing to the smallest pin, is a fascinating world of physics, material science, and safety. If this deep dive into the hidden mechanics of flight has captured your curiosity, make sure you subscribe and hit the notification bell so you don't miss our next exploration. And let me know in the comments, what other piece of aviation technology do you want us to break down next? In the end, every safe landing is a silent testament to incredible engineering. It's a dance between a pneumatic spring and a hydraulic damper, choreographed by a simple, tapered metering pin. This pin, buried deep within the landing gear, has no computers and no active controls, yet it flawlessly helps manage the immense forces at play. To me, that's the real beauty of it. Not magic, but exact calculations and a deep respect for the laws of nature. The next time you experience a smooth touchdown, you'll know that a small, ingenious pin was working perfectly in the dark, turning a potential disaster into a routine arrival.